Hey guys, so this video is about partial fraction decomposition. The only place I can think this comes up is in Calc 2. You use it for an integration technique. I'm going to start by going much the same way that factoring and multiplying are kind of reverse operations. What we're going to do here is a reverse operation, is something we learned back in 95 or 98. So I'm going to do one of these just to kind of remind you of what they look like going the one direction, to hopefully get you to see what it is we're trying to do. So if I have a rational expression and I'm trying to add it, what I need to do is get a common denominator. So I'm going to multiply this side by the x minus 1s, and this side by the x plus 1s, or x plus 2s, sorry. And so then that's going to look like 2x plus 2 plus 3x minus 1, all over this common denominator now of x plus 2, x minus 1. And then I distribute and collect terms. So that'll be 2x plus 4 plus 3x minus 3. I'm just going to write LCD here for the sake of time. And then 2x and 3x makes 5x. And 4 minus 3 makes plus 1 right there. That's x plus 2, x minus 1. And so what we're doing in this section is we're given this, and we're going to try to take it back to here. And so if you thought it was bad this way, these definitely get a little bit involved. We're going to have two different methods for approaching it. And so I'll show what I'm going to do is I'm going to take this example, which is a fairly friendly one, and then do both methods with the same example so you can kind of compare them side by side. So here we are. So this is the same thing I got back here, so I should get this answer. And so what we're going to do is we're going to set this up saying, you know, if I have this, I had some fraction that had to have had this denominator, x minus 1. And I had some other fraction that had to have had this denominator. And then up top, because I know I'm multiplying by an x, because to get the common denominator I'd have to do x and x. That means this top, for it to be linear, these have to be constants. And so we're going to see that when we kind of formalize this, that the degree of the numerator is always going to be 1 less than the degree of the denominator when we're adding these things. And so since this is a constant, since this is a linear equation, it just gets the constants a and b. And more on that to come. There's a whole big box of stuff for that. So then once we do that, what we're going to do is, bring my notes over. Okay, so once we do that, then we're going to multiply both sides by the LCD. And so that's going to look like, over here I'm just going to write LCD for the sake of space. And then over on this side, it's going to be x minus 1, x plus 2. And this is our first method, but this step is the same for either method. So when I pick up the other one, I'll pick up here. So here the LCD would just cancel all of this, and I get the 5x plus 1. On this side, the x plus 1's cancel, so I get a times x plus 2 plus b times, and then those would cancel, so the x minus 1. So they each get the other one, basically. And then from here, I can go a few different directions. And so for method 1, what we want to do is we want to use the zeros, the things that would make the denominator undefined. We're going to plug those in and evaluate. And you'll see how, let me do it, and then you're going to see why that was actually a good plan. So I'm going to let, first I'll let x equal 1, and that's going to, because this one's 0. So that'll be 5 times 1 plus 1, and then 1 plus 2 right there. And so that's why you want to do it, is because it knocks out one of the variables, because that got multiplied up. And so that's going to leave me a single variable problem, and I can actually solve that. So 5 and 1 will make 6. This will be 1 plus 2, so that'd be a 3a. And then 1 minus 1 is 0b, so that term drops out. So now I know that a equals 2. And that's this piece back up here, that's that constant. Now I'll use the other 0, x equals -2, so I'll be 5, -2 plus 1, and then a -2 plus 2. So we could just not write that piece, but just for me to show it. So this would be -10 plus 1 is -9. And then this would be a times 0, so that drops out. So that's equals -2 minus 1 will be -3b. And then dividing the 3 over, I get b equals 3. So then my answer, the decomposition of the fractions, is going to be a is 2, so that's over the x minus 1 term, and then b is 3, so that's over the x plus 2 term. So it wouldn't have mattered which order I wrote these in, it just meant like if I'd switched these, then my a would have been b and vice versa, but I would have gotten the same expression at the end, so the order does not matter. And so just kind of going back to this one, just to remind you that's where we started, and so that's where we've gotten to here at the end. So that's our first method. And this method is good when there are lots of zeros. So if you have most of the zeros you'd need, so say you have 3 constants, or three letters that you have to find, and they're 2 zeros, then this is a good method. So if you have most of them, this is the way to go. So method 2 works better if you don't have any of the zeros or not very many of the zeros. And the first step is the same. So I would set this up exactly the same, a x minus 1, and then plus b x plus 2. And then I would clear the fractions the same way, and I'll just get that written out right up here. So 5x plus 1, and I'm going to grab so this is a x minus 1, and then b x plus 2. So then in this method, in the first method, I left it like that because it was nice because I could see these things would zero out. But in this method, I want to distribute. So that's where they change. So this will be 5x plus 1 equals ax minus a plus bx plus 2b. And then I want to group up my x's and my constants. So that's going to look like 5x plus 1. Important not to lose that side of the equation. Ax plus bx, and then minus a plus 2b. So then what I'll do is I'm going to factor out an x here, and I'll show you, it'll make more sense once I do it. So this is going to equal, so I'm factoring the x, but I'm going to write it as a plus b times x. And then, so I'm writing the x second. And then this is going to be plus a plus 2b. And so what we do then is we match up the two sides of this equation. So the 5x goes with the a plus bx. So these are both the x terms, the linear terms. So what that means is the 5 has to equal that a plus b. So then I can go a plus b equals 5. And then the 1, so it has to equal the plus all that stuff. And we could think of this as x to the 0, x to the 0. So we're just saying the 5 goes with the x coefficients, and then the 1 goes with the x to the 0 coefficients. And so this would just look like negative a plus 2b equals 1. And so that's why this is in this section, is there's our little system of equations that pops out. This one comes out pretty nice. The a's are all ready to cancel, so I'll just go 3b equals 6. And so that means that b equals 2. Once I know b equals 2, I can toss it back into either equation. First one looks easy. So moving that over, I get a equals 3. And so that's the same thing I got in the last one. So we'd have the 3 over the x minus 1 and the 2 over the b, or the x plus 2. So that's the second method. So like I said, if you don't have too many zeros or you don't have any zeros, this one's better. If you have the zeros, the other one is the easier way to go. Okay, here's this kind of big dicey box from the notes of how to get these things set up. And once you see it, it's actually pretty easy, but it's a little bit confusing at the start for sure. And then here's what I was saying in terms of the zeros. Method 1, if you have lots of zeros. Method 2, if you have not too many zeros. So this is, we have four things, and they kind of come in pairs. So we have non-repeated linear factors. So an example of non-repeated linear factors would be x plus 1, x plus 2, x plus 3 in a denominator. So there's no squares. Everything is x to the first, so that would be non-repeating linear factors versus repeated linear factors. So this would be like if I had x plus 1 cubed. That would be a repeating linear factor. So the way we set these up is whatever this is up here, doesn't matter. I would have a over x plus 1, I would have b over x plus 2, and c over x plus 3, and so on, as far as I need to go with that. And so each one just gets its own constant. Again, it's always 1 degree less than the denominator, so the numerator is constant, the denominator is linear. For a repeated one, again, this would be have some numerator up here. What we do is we set up 1 for each possibility. So it's possible there's an x plus 1 term. It's possible there's an x plus 1 squared term. And then I have to have, because it's a cube, a 1 plus x. Oops, I'm writing these ones. I totally don't mean these ones, sorry. X plus 1, I'm just saying 1 a bunch, cubed. And so then this would also be a, b, c, sorry about that. And so it's setting up very similar to this. We just have to allow for every possible denominator that could result in this. So to the first, to the second, and to the third. So that is this one and this one. So now here we get non-repeating irreducible quadratic factors and repeating irreducible quadratic factors. So it's kind of the same idea as up here. So an irreducible quadratic would be something like x squared plus 6. That doesn't factor. So if it factored, I'd factor it down, and I would get two either non-repeating or repeating linear factors. So if I had this, I would set that up as, actually, let's say I have a combination. Let's say I have a linear factor and a irreducible quadratic. So then I would have an a over the linear factor. So that's just like this. This is just kind of the most basic one. And then over the quadratic, I need a linear term because it has to be 1 degree less. So that would be, in this case, bx plus c over x squared plus 6. So linears get just a letter, just a constant. Quadratics get a linear setup. So a repeating irreducible quadratic, that would be, something like if I have, again, it's just whatever's up here, doesn't matter on this side. If I had x squared plus 4 squared. So that would set up ax plus b over x squared plus 4, and then plus cx plus d over x squared plus 4 squared. So it's the same thing we saw up here. It's just now it's with the quadratics. So that's our first step, is to set up this right-hand side. They'll give us a side, and then we have to set up the right-hand side so that we can clear fractions and then pick one of the methods. So let's see that with a few examples. Okay, so we got this. So I have two linear factors, and this one repeats, this one doesn't. So for my first one, I'm just going to have an a over x plus 2. And then I need a b over a single x minus 1, because that could be there. Maybe it isn't, maybe it is. And then c over x minus 1 squared. I know I have these two for sure, but this one is iffy, because if I didn't have it, that's still the LCD. If I do have it, it's still the LCD. So I have to allow for the possibility. So now I'm going to use this LCD to clear the fractions. Again, on this side, I'm just going to write LCD for the sake of space. And then on this side, I'll write it out so you can see a little better. So x plus 2 and then x minus 1 squared. So here, this all cancels, and I just have the x squared plus x. And then that's going to equal a, and it's going to, basically whatever's here isn't going to be on the next line because it's what's canceling. So it's a, and then x minus 1 squared, and then plus b, so one of the x minus 1's is gone, so x plus 2, x minus 1. And c, the x minus 1 squareds cancel, so c x plus 2. So in this one I have 3 things I'm trying to find, and I have 2 zeros. So I'm going to use method 1 because I have more zeros than not. So then that's generally the easier way. And so this one, if I set it up equal, it's going to also come out to a 3 equation 3 unknown, which is not nearly as nice to solve as a 2 equation with 2 unknowns. So that second method can get, the higher this degree, the more issues there can be in terms of solving it. So I'm going to let x equal, how about 1 to start, and we'll knock out the 1's. So that'll be 1 squared plus 1 equals, that drops out because 1 minus 1, that drops out because 1 minus 1, 0 times all that's 0. So that equals c 1 plus 2. So this time I'm not going to write all the stuff that isn't there because that makes it look a lot friendlier. So that's going to be 2 equals 3c, and then dividing over I have c equals 2/3. And then I'm going to let x equal -2, so that will be -2 squared, and then plus or minus -2, so I'll just write -2. And then a stays, so a times -2 minus 1 squared. -2 would knock out b and c. So this is going to be 4 minus 2 equals 3 squared would be 9a. Or 2 equals 9a, or a equals 2/9. And so then that took care of our zeros, so then we have to come up with one more to try. And what we can do is put in c and a once we have the expression, and then use that to solve for the last one. So I'm going to let x equals 0. And with these fractions, it's not going to be nice no matter what, but that's probably as good as we're going to get. So here I could pick 0, plugging in 0 on this side gives me 0. And then this would be a, and then 0 minus 1 squared, plus b, and then 0 plus 2, 0 minus 1. I'm just writing this out to make sure everyone knows where I'm plugging in, and 0 plus 2. So if I'm writing this for not to show where I'm plugging this in, I would just go a, so that would be plain a, because that's 1. -1 squared will be 1. This will be 2 times -1, so minus 2b. And c would be 0 plus 2, so 2c. So that's how I'd write it for me, but that's the math I did. And then I know a and c, so I can plug those in. And 0 equals 2/9 minus 2b plus 2 times 2/3. So that's going to be 0 equals 2/9 minus 2b, and then 4/3. And so I'm going to make this 3/3 right here. And then I'm going to add this 2b over. I'm going to sneak up here with it just because I'm running out of room. So then bringing this over, that becomes positive 2b equals 2/9 plus 12/9, or 2b equals 14/9. So you can see why we don't want to do this if we don't have zeros, because it's not that great. And then multiply both sides by 1/2. Although honestly, if these weren't fractions, it would be a lot easier. That cancels, and I get b equals 2 goes into 14 7 times. So b equals 7/9. And so then our answer would just be this right here for the a, this right here for the B, and this right here for the C. On the computer, I think maybe they have boxes set up for you already. I'm not positive though, or maybe you do have to. I think you do have to type it in, because if they set up the boxes, they'd be telling you how to set it up. Okay, so then this one is a non-repeating irreducible quadratic, and it also has a linear term there too. So this is going to be a over x, and then plus bx plus c over the quadratic piece. And then I'll do the bit with the LCD to clear the fractions. So I'll just do here, and then this is x squared plus 2x minus 6. So on this side, everything cancels, and I just have 8x squared minus 12. And on this side, the x's cancel, and I have a, and that's going to be times x squared plus 2x minus 6. And then here, this cancels, so I'll have x times the bx plus c part. And so this time I have 3 things I have to find, but only 1 0, so I'm going to use method 2. So cleaning this up, actually before I do that, I'm going to I do have 1 0, which is x is 0. So I'm going to let x equal 0, and I'm going to get one of these letters, because I can at least get, if x is 0, that knocks out this piece. So it's going to let me get a. So 0 right here would give me 8 times 0, so only that negative 12 survives. And then a, and 0 squared plus 2 times 0 minus 6, and this piece drops out. So this is all really just negative 12 equals, that would be negative 6a. I keep showing this step, and it just seems like it makes it so much harder. If this is 0, you got negative 12, and these are gone, so negative 6 times a. So I would try to think of it that way. Anyhow, that gives us that a is 2. Which is actually a big advantage, because that's going to take us from a 3 equation 3 unknown to a 2 equation 2 unknown. So then I can do, once I know a is 2, I'm going to plug that in right here. I'm going to have x squared minus 12 equals, so this is now a 2, and then x squared plus 2x minus 6 plus x bx plus c. And then I'm going to distribute, and I'm going to get this thing organized a little bit, and I'll show you what I mean by that. So running the 2 through, I get 2x squared, I get 4x, and then minus 12. And then bx squared plus cx. So what these have the b and the c, these have coefficients, so I want to get all this over here. So what I'm going to do is subtract 2x squared, subtract 4x, and add the 12. So minus 2x squared, I'll slip the 4x in between there, and plus 12. This is going to work pretty good. So we got 8 minus 2, so that would be 6x squared, and the minus 4x comes along, but then these 12s drop out, and then that's left with bx squared plus cx. And so what that means is that, so since this is 6x squared equals bx squared, then b is 6. And since minus 4x equals the cx, 4's the negative 4 is c. And so this time I have enough space to write my answer. So right here, let me write down what I just said. So b equals 6, and c equals negative 4. So my answer would look like a is 2x, I'm just plugging right back in here, plus 6x minus 4 over x squared plus 2x minus 6. So that's how we go back and do the answer. Okay, this last example is irreducible quadratics. So this will look like ax plus b over x squared plus 16, and then, oops, that should be a plus cx plus d, so I just do another linear term, over x squared plus 16 squared. And then I'll multiply both sides by the LCD. So over here again, I'll just write LCD. Out here it's the x squared plus 16 quantity squared. So this whole side cancels, and I got x cubed plus 1. And then this 1 would cancel and 1 would survive, right? So this is going to be ax plus b, and then x squared plus 16. And then right here, this would cancel entirely, so just cx plus d survives. And so then I'm going to FOIL, and I'm going to kind of, again, get things organized. So ax times x squared will be ax cubed, ax times 16, so that's 16 ax, and then bx squared, and 16b, and then cx plus d. So what I want to do is go cube, square, linear, constant. And so, and then on this side, I'm going to include some zeros over here. I'm going to show the missing terms. And once I get it all written out, you'll see how come I'm doing that. So this is going to be x cubed, and you can think of that as a 1x cubed plus 0x squared plus 0x plus 1. And then on this side, I'm going to have ax cubed and then plus bx squared. And for the linear ones, I have, shoot, I'm going to have to write this out one more time. Let me get these grouped, or it'll be really hard to follow what it is I did. Okay, so one more round of that. So 1x cubed plus 0x squared, 0x plus 1. And then here, we have that, and that. And then we have factor the x out, but again, I'm going to factor to the back just because it looks better. So 16x plus c x. And then here, 16b plus d. So then matching up the coefficients, I'm going to have 1 makes a, and then 0 makes b, and then this 0 in front of the linear, right? So that's the x is matched, so I'm matching the 0 to the 16a plus c, and then back here finally this 1 matches all of that. So let me get all that written out. So okay, so we have a is 1, cool, good to know. We got bx squared equals 0x squared, so b is 0, also good to know. And then here we're going to have 16a plus c equals 0. That doesn't mean they're 0, that just means they equal 0. And on this last one, 16b plus d equals 1. So, since I know a and b already, that makes the rest of this pretty easy. So if a is 1, I'll plug that right here, and I get 16 times 1 plus c equals 0. So c is going to be negative 16 when I bring that over. And then right here, I can do b is 0, and if b is 0, then I know d is 1, because this would drop out. So that's going to give me, to write out my answer, a is 1, so this would be x. I'll write 1x just for emphasis. B is 0, so I don't need that term, and that's over x squared plus 16. And then here, cx plus d, so that's going to be negative 16x plus 1 over x squared plus 16 quantity squared. And that wraps up partial fractions.